time, 15 minutes. Thank you.
Thank you very much, Professor. I think you did a very clear and brief introduction about your recent research regarding the impact of the pandemic. Thank you. So next we will have the second speaker, who is a research associate in Faculty of Mathematics, University of Cambridge. Let's welcome Dr. Rajesh Bhagat. I'm hoping I'm reading it correctly.
Sorry.
All right, the floor is yours.
Yeah, thank you. I hope you can see my slide soon.
We cannot see
Okay,
it now.
you can see my screen, right? Could you see my screen?
Yeah.
Okay.
No. Just,
No?
No.
Okay. Hi everyone. I'm Rajesh Bhagat. I'm based at Department of Applied Maths and Theoretical Physics here at Cambridge. I just wanted to ask you in presenter view, can you see my slides, or you can see also the next slides and so on? Sorry.
We
Hello?
can see the next one. We can
Okay.
see the next one.
Okay, you can see the
And
next one as well.
Click the button at the top.
Okay, it's fine. I can now you can see my slide, right? So
Yes,
hi everyone, I'm Rajesh Bhagat. I'm based at maths here at Cambridge, and I'm going to talk about displacement ventilation, a viable ventilation strategy to prevent airborne disease transmission. Building ventilation has been studied in the context of energy efficiency, thermal comfort, and sustainability. But with COVID-19, as we all know, that building ventilation was recommended to be increased to reduce the airborne disease transmission. However, we also know that increasing ventilation implies we will use more energy, and it would be energy inefficient system. So essentially, we need to build resilience in our system. We need to build resilience in our built environment, particularly because most of the buildings where we will live has already been built. And new buildings are also been built all the time, and we need to understand ventilation and create a robust ventilation strategy to reduce our energy needs. As we know that 30% of total global energy is consumed in buildings, essentially in heating, cooling, appliances, and so on. And we have a huge scope to reduce our energy consumption there, and in order to achieve the net zero target, it is very important to do so. So I will talk about ventilation modes. First, mixing ventilation, because this is kind of most preferred mode of ventilation. In mixing ventilation, and in mixing ventilation, essentially, I will talk a little bit more about it later. But in mixing ventilation, is analogous to having a bath in a bathtub, where you could be as clean as the water in the bathtub, which is contaminated with your own pollutant. Whereas displacement ventilation is another strategy, and I would show you in my next slides, that in variety of situations, displacement ventilation arises naturally, and it is very hard to avoid that. In displacement ventilation, it's analogous to having a shower. So you will be rinsed with clean water continuously, and potentially your contaminant can be taken to the upper level, and from there it can be removed from the indoor space. So it is very promising from the point of view of removing the indoor air pollution and contagions produced in indoor environment. However, I will show you that displacement ventilation particularly has been recommended not to be used in hospitals, and due to the reasons which are yeah, and I would like to address those things. So here first I would like to show you these two videos. In the first video, what I'm going to show you is an unventilated space which is filled with smoke, and in the smoke a person will stand soon, and this person is going quietly there without disturbing the flow. And I would like to show you the flow pattern produced by the heat or the body heat of this person. So as soon as he stands in this illuminated region, you could see that the smoke, which acts as a tracer, is completely drawn with the body plume, and this is quite high speed actually. I will show you in my next slide that the velocity around this person is not low, and similarly here this person is sitting, Professor Stuart Dale essentially is sitting in a ventilated space. So this is mechanically ventilated space where he is sitting, and still you can see that his body plume rises up. And I would argue that thermal stratification is kind of inevitable in most of the scenarios, and mixing is very difficult. So let me show you with this slide. So here what you are seeing is the typical velocity of the air, which is due to the heat body heat produced by the person. And this is just theoretical value. And you can see that it is of the order of 0.5 to 0.2, 0.3 meters per second. Whereas even in 10 ACH, air change per hour, in a space, the bulk velocity of air would be of the order of centimeters per second. So you can imagine that until and unless you sit right under the vent, the body plume will rise and thermal stratification will be created. And it is also it can also be realized by just considering doing a simple energy analysis. So if you take a stratified room and calculate the energy in this stratified room, and then if you want to have this room completely mixed, you calculate the potential energy of this room, you will find that you will have to inject a lot of energy just for mixing. And why I am talking about displacement ventilation, despite having some issues with this, which I would talk in my next slide, is because if you remember, during the summer in COVID-19 2020 and 2021, it was advised that we open the doors and windows of our house. If you open the doors and window of our house in urban environment where wind is mostly unavailable in single-sided room openings, we essentially create displacement ventilation actually due to the thermal energy which is provided in the room due to body heat, etc. But displacement ventilation in case of hospitals and other cases has been highly criticized and has been highly discouraged. And I mean, there are a number of papers about this, and rightly so. In this paper, the authors have shown that if a person breathes at this particular level or the bed height, the air or the fluid which is exhalation fluid which is produced by breathing stratifies at a lower level and in the breathing zone where we don't want this fluid to be. So we want breathing zone to be clean, whereas they have indiscreetly showed that they have clearly shown that this fluid gets trapped in a layer which they call as lockup layer, and therefore it was advised not to use displacement ventilation was discouraged to be used in healthcare settings. And here I'm showing you another example. So this is our CMS atrium. We filled the space. This space has natural displacement ventilation. We fill the space with smoke, and as you can see that literally stratified, the smoke gets trapped into a layer at a breathing height, and we really don't want this. So this is called a lockup effect, and due to this displacement ventilation has been discouraged. But during the pandemic, I wrote 2 papers, and in those papers, I have shown that what is the exhaust mechanism for this lockup layer is, and how we can remove this, and how we can utilize displacement ventilation, or how we can use natural ventilation for our advantage, both from the point of view of energy efficiency and removal of contagions. So I would discuss that in my slide now. So here I'm going to show you this video. So we carry out experiment in water tank. So essentially we can scale down the system in water tank, and we can carry out experiment in water tank which can be translated into real room. So what you'll see in this is a person, a mannequin standing in stratified, and the body plume creates a stratified environment. So there are two openings, one at a lower level and another at upper level, and this is a displacement ventilated space, and I have dyed fluid release as exhalation fluid, and as you can see that this dyed fluid is locked up in a layer below the stratified layer, which is completely undesirable until and unless somehow we can keep it above the person's height. Now you can imagine the scenario in a hospital. So a person or a doctor or a nurse is standing and a patient is lying down on the bed. And it is very highly likely that this person, until and unless we understand and we do something about it, the lockup layer will be at a breathing zone where we don't want it. But what I want to show you in this video also is how, if we understand the exhaust mechanism for this lockup layer, we will be able to find the mitigating strategy, and we will be able to keep it above the head of breathing zone. So this is the same video at a high speed. What you will see is this red dyed fluid gets trapped into, get entrained into this body plume, and then it is taken to the upper level, and from there it is exhausted from the building. So we understand the mechanism. In the paper we proposed that how this can be done, and I'm going to show you in my next slide. So one of first thing was during the COVID crisis, we said that, I mean, in this video, it will be clear that if a person wears a mask, most of the fluid, the exhalation fluid this person releases, remains close to the body plume. So here this person is laughing. When he is breathing, everything almost kind of remains in his body plume. Whereas when he laughs without mask, the fluid, exhalation fluid, goes far away from his body plume, and then it can produce a lockup layer. Whereas if a person wears a mask, this lockup layer problem can be solved. But of course, in normal time, we don't wear mask, and we need to understand in order to develop robust, resilient infrastructure, we need to understand the lockup layer, and we need to find out the mitigating strategy. So in my video, as I have shown, that a similar thing I'm showing you here in this sketch, that the cold fluid enters at a lower level, hot fluid comes out of the upper level, and this plume here shown in red is the hot plume, whereas the plume in green is shown as the less hot fluid, which is stratified below the hot fluid. And then essentially what happens is this fluid gets entrained into the hot plume, and then it is taken to the upper layer. So the lower second stratified zone, the green zone here, which you can see where I am moving my arrow, gets entrained into this plume, and then it can be removed from the space. And if you have looked into natural ventilation scenarios or displacement ventilation, in displacement ventilation, the height of the stratified zone is essentially defined by the height of the room and height of the and the area, opening area. And in case of mechanical ventilation, mechanically displacement ventilated space, it would be a function of flow rate or the ventilation rate and height of the building, essentially. So we can change the ventilation rate to keep the stratified layer, or we can change the opening size to keep this lockup layer above the breathing zone, and it will produce clean environment. So so essentially in these papers, in these initial papers, we showed that we know the mechanism. There are ways to keep it above, and we need to study further, essentially because the natural ventilation is the way to go to deal with climate crisis, etc. And we need to understand this. And we so to conclude with I would like to say that green buildings are crucial to achieve net zero and to limit the climate crisis. Displacement ventilation is often the naturally arising ventilation scenario, whether we want it or not. If implemented correctly, displacement ventilation can reduce the risk of airborne disease transmission. Of course, we need to understand the outstanding issues such as effect of people's movement, which has not been studied as much. Distribution of heat source. I showed you that most of the time, if we have a concentrated heat source, we will create a plume, and then we will create displacement ventilation sort of scenario. Whereas if we have a constant heat flux from the floor, we will create a mixed environment. So, I mean, it really depends upon the distribution of heat source in indoor environment. We need to understand those things, and in that context, we also understand. We also have to understand the lockup layer, etc. And these things need to be studied. And as I said, that during the summer, the recommendation was to open the windows and doors. But as we know now, that during the winter, which winter is coming in northern hemisphere, during the winter it would be impossible, and the energy need will, if we really want to ventilate the space continuously, the energy need will increase. So for winter time ventilation, air filtration and heat recovery would be a very important aspect to natural ventilation, and we must study those things. And here what I'm showing you in the picture which you are seeing in my concluding slide is one of the sketches of Florence Nightingale. And the recommendation which Florence Nightingale gave almost 200 years was actually recited by many people during the pandemic. And those recommendations remains valid for resilient built environment, high ceiling, etc. But the lamp hanging here also tells us that maybe we can, what we can do is we can increase the buoyancy of lockup layer and take it at a higher level much faster. So there are a lot which can be done, and we need to study those things. And my study is focused in these areas. So thank you very much. And if you have any question, I would be happy to take your questions. Thank you.
Thank you. It's very nice demonstration of how the meditation might influence the transmission of virus and the items in the air. We will have the discussion at the end. So thank you again, and we will may have the question and answer later. Thanks again. Okay, our next speaker is from Sun Yat-sen University, who is the Vice Dean of Urban Climate and Building Environment, Professor Jian Hang, who is also talking about